When you stir a spoonful of sugar into a glass of water, you watch a solid completely vanish into a liquid. The water looks exactly as it did before, but the sugar is still there, hidden between the molecules of the liquid. This everyday observation raises a specific physical question. What mechanism dictates exactly what happens if you keep adding spoonful after spoonful indefinitely? At the microscopic level, the solvent acts like a structured environment with a limited number of seats available. The sugar, the solute, acts like a crowd of passengers looking for a place to sit. When these passengers easily find empty seats, the solid dissolves into the liquid. This specific state is what chemists define as an unsaturated solution. As long as there are remaining empty seats in this microscopic structure, the liquid will continue to accept and hide more of the solid material. Dissolving is essentially a physical matching game of microscopic space. But because that space is finite, there is an inevitable moment where the liquid simply runs out of room. Eventually, you hit a turning point in the glass. The sugar stops disappearing, and instead it begins to pile up uselessly at the bottom. This liquid has reached maximum capacity at its current temperature. This is a saturated solution. Every microscopic seat is occupied. Unlike a concentrated solution, which just has a high solute ratio and may have empty seats, saturation is a strict structural limit. Under normal conditions, saturation acts as a physical wall. Once every seat is filled, the liquid will refuse to dissolve any further solid, no matter how much you stir. So how do you force a completely full, saturated liquid to absorb even more solid? To change the capacity of the solvent, you have to actively alter its physical properties by applying heat. This solubility curve shows how heat increases capacity. Heating makes solvent molecules move faster and spread apart, creating new, temporary seats. With this added energy, a cold, saturated solution becomes unsaturated, allowing it to dissolve more material as temperature rises. Temperature is the primary variable here, actively expanding the physical limits of the liquid and resetting the rules of saturation. To see the most dramatic effect of this process, we can dissolve a massive volume of sugar into boiling water until it hits the saturation limit at that high temperature. Then, we slowly and carefully cool that mixture back down to room temperature. This must be done without any bumping or vibration that might disturb the liquid. As it cools, extra seats vanish, but the sugar remains trapped. This creates a supersaturated state, holding more solute than normally possible. This state is highly unstable. The excess solid is waiting for any physical trigger to escape. That trigger is a single tiny seed crystal. Dropping it into the mixture provides the escape route the trapped particles have been looking for. The moment the crystal touches the liquid, the excess solute crashes out of the solution in a rapid geometric chain reaction. We see this process in nature and our kitchens. It is the mechanism that creates rock candy on a string, and it is exactly why old honey eventually turns crunchy as its sugars settle out of the liquid. Saturation is a temperature-dependent balancing act between dissolving and solidifying. It shows us that while liquids have strict physical limits, we can use the laws of thermodynamics to temporarily expand those limits and witness the physics of crystallization in real time.